Welcome back for chapter 4. This should be a short chapter. There's only one section we're covering in this chapter, but that one section is a pretty big idea. It's the basic concepts of probability. Now, depending on what courses you've taken before, I'm hoping that for most of you, this will be some kind of a high-level review, because this should be material that you've covered before. In your 142 class or in your college algebra, at some point you should have seen this before. All right, so let's go ahead and get started. Take a look at our concepts. Our key concepts for this section is the idea of how to interpret probability values. Like, we won't be calculating many of them. We will be calculating some, but it's more about interpreting what they mean. Remember, probabilities are always a number that is expressed something between 0 and 1. And our job is to be able to go, okay, what does that mean that the probability is blah, 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 blah? Such as if you had a probability of 0.001, or if you prefer as a percent, a 0.1%. Well, I would hope that you could look at that and tell me whether that is a common thing to occur, an uncommon thing to occur, right? And then we'll also talk a little bit about odds and how they relate to probabilities. Odds are commonly used in situations where we're talking about some sort of gambling, lotteries, throwing dice, playing cards, those sort of things, betting on football games or that kind of stuff, which, again, to be clear, I'm not advocating, but I know people do it, so I'm here to explain the math of it. All right, so let's start out with some review of some terminology. Our probability experiment, that is going to be the thing that we're going to do that will result in outcomes or measurements or responses. So it's the action or trial through which those results are obtained. Okay. So the probability experiment is the flipping of the coin, the rolling of the die, the spinning of the spinner, picking a card from a deck. It's the thing that you do, and then you get a result from that. Right? That result is something we either count or measure, or if it's like a survey, it's a response that we mark down. Okay. Those things that happen when we run the experiment, we call those outcomes. A single outcome is the result of a single trial of an experiment. Okay. If you take all of those outcomes and lump them together in one big pile, we call that thing the sample space. It is the set of all possible outcomes for our experiment. So what I mean by that is, let's keep it real simple. Let's say that our experiment was to flip a coin. Well, an outcome could be coin lands heads, or an outcome could be coin lands tails. And if we take both of those outcomes and put them together in a set, heads, tails, we have now created the sample space for the experiment. Heads is an outcome, tails is an outcome. That set contains all of the possible outcomes, so we call it the sample space. Okay. An event, oops, I don't want that, I want this. An event is a subset of a sample space. Now, it's kind of hard to talk about events for that experiment, so let's take a look at another one. Suppose that our experiment was to roll a die. Okay, now just really quickly. When it doesn't say, it means it's a 6-sided die. There are dice with more or less sides. There are 4-sided, 6-sided, 8-sided, 10-sided, 12-sided, 20-sided, and other dice out there. If it doesn't say, it's a 6. Okay? Our sample space for this experiment would be 1, 2, 3, 4, 5, and 6. Okay. Our sample space is the list of everything that could happen if we roll a die. An event is a subset of a sample space. So an event could be something like A could be the event 2, 4, 6. Okay? Or in words, you rolled an even number. It's a subset of the sample space because it's not just one thing, it's several things from the sample space. Right? So subsets of sample space. All right, so let's take a look at some examples. Here are some experiments, and our job is to come up with the sample space for these experiments. All right, our experiment is going to be guessing the initial of a student's middle name. So my sample space, S, needs to be the set of all possible outcomes. Well, I think that's just going to be A, B, C, Z. Because that would be all of the ways that I could guess the initial of a student's middle name. Now we are making some assumptions here. We're assuming the student has a middle name, because if they didn't have a middle name, then I'd have to add an outcome in there that would be no middle name. So I'm assuming they have a middle name. I'm also assuming they only have one middle name, so I'm going to have to worry about one letter to guess the initial. Right? All right. What if the experiment was to draw a card from a standard deck? Well, what's the sample space there? Well, if I tried to write it out roster method like this, I would have the 2 of hearts, the 3 of hearts, the 4 of hearts, and so on and so forth. But I don't know that I can do this. I don't know if I can ... a deck of cards away, because it really doesn't... dots don't work like that. The ellipsis, it works like this, where you can set a pattern and tell it where to end. Or dots work if it was like 1, 2, 3, ... to mean it just goes on forever. But dots don't work with decks of cards. So I don't think I can list it like that in the roster method, but I could say the sample space is all 52 cards. Right? Again, I'm making an assumption here. I'm assuming that everyone in my audience knows that a standard deck has 52 cards, 4 suits, those suits being the hearts and the diamonds, which are the red suits, the spades and the clubs, which are the black suits, that there are number cards, which are numbered 2 through 10, and there are face cards, which are jacks, queens, and kings, and then there are aces. Aces don't have faces. I'm assuming everyone knows that. I'm not sure if it's a good assumption or not, but I'm going to go with it. All right. This last one's probably the hardest of all of them, not because of anything other than how we're going to have to define this. Let's say our sample space needs to be the sample space for the experiment tossing 2 coins. Well, I think I can list this one. Now, I don't think anyone's going to argue with me about that one possible outcome would be that both coins land on heads. Another possible outcome would be that both coins land on tails. Here's where things are going to get tricky. Most people will agree that one possible outcome is heads and tails, and here's the one that people aren't going to like. Tails, heads. Are these two different? Whoa, undo that. Are these two different? Is the outcome heads, tails different from the outcome tails, heads? Well, if we think about it, and maybe if you took a biology course at some time, you made one of these Punnett squares for gene expression. But if you think of this as coin 1 and this as coin 2, coin 1 could land heads, tails, coin 2 could land heads, tails, which means that one outcome is heads, heads, one outcome is heads, tails, one outcome is tails, heads, and one outcome is tails, tails. Which means that our sample space needs to have 4 things in it because there's 4 possible ways. These two are different. Right? Maybe a way to think about it to make it make sense to you is, suppose that this was a quarter and this was a dime. Right? Then this outcome here in the lower left would be dime, tails, quarter, heads, whereas this outcome in the upper right would be dime, heads, quarter, tails, which that would make them seem more different. Maybe think about it that way. Right? Here's a really hard one. Let's say they were taking a survey and we're going to ask people their blood type. That is, are they O, A, B, or AB, including whether they are Rh positive or Rh negative. How many outcomes are in that sample space? Well, I know what some people would want to do. They'd want to say that sample space is O, A, B, AB plus and minus, but that's not how it works. That's not a possible outcome. No one is going to answer that their blood type is positive. No one's going to answer that their blood type is negative. They're going to have to attach that to something. So I don't think that's the sample space. I think it would be more appropriate to think about how someone would identify their blood type. Like someone could say that they are O positive, or someone could say that they are O negative, or someone could say that they're A positive, A negative, B positive, B negative, AB positive, or AB negative. So it looks like there's 8, that is a horrible B, 8 different possible outcomes in that sample space. Now, one thing about this one that's different than the rest of them is here, here, and here, we wrote sample spaces where everything had the same chance. Like if I was just randomly picking an initial for a student's name, I could pick any number or any letter and it had the same chance of being picked. If I pick a card from a well-shuffled deck, every card should have the same chance of being picked. If I flip coins, all 4 of those outcomes should have the same chance of occurring. These aren't all equally likely. There isn't just a 1/8 chance. What the heck? There's no G in chance. Chance of someone having each of those blood types. Right? So sample spaces don't have to be equally likely. We like it when they are. Right? A simple event is an event that consists of a single outcome in a sample space. If it has more than one outcome, we just call it an event. Right? So what do I mean by that? Right? Well, when rolling a single die, the outcome of 5 is a simple event. But the outcome of an even number is not a simple event. We would just call that an event. And I want to show why this is true. So if my experiment is to roll a die, my sample space, things that could happen, are the numbers 1 through 6. Right? Even number, and I'm going to call that A, event A, would have 3 things in it. 2, 4, and 6, because there are 3 numbers in the sample space that are even numbers, the 2, the 4, and the 6. So that is not a simple event because a simple event only has 1 thing in it. And if I called event B, roll a 5, well, B is just that. It is just a 5. Well, that's 1 thing from the sample space, so we would call that a simple event. Right? We don't see this phrase a lot, but if you do run across it, I want you to know what it is. It just means that someone set up an experiment and is talking about an outcome, a single outcome, and wants to call that single outcome the event for which they want to calculate probability. Okay? Some notes about probability. I'm hoping you remember this. We use capital P's to denote probability. Right? We tend to use letters from the start of the alphabet like A, B, and C to denote events. So then when we write something like this, the reader would look at that and go, oh, there's a P, parentheses A. The P means probability, so A is the event, so that is the probability of a event A occurring. Okay? I'm hoping also that you remember that probabilities have to be numbers between 0 and 1, and that the probability of 0, so if the probability of some event E was exactly 0, that means it cannot happen. On the other end, if the probability of an event E was 1, it means it absolutely will happen. Okay? For example, if I were to ask what is the probability that I will die, well, the probability I will die is 1. It's going to happen. You notice I didn't say when. I just said it's going to happen. Okay? Something that has a probability of 0 is a little bit harder because you have to come up with an event that absolutely can't happen. Right? It's not about it's unlikely. It means it absolutely can't happen. So something that can happen is like, what is the probability that cats will fall from the sky? Well, I don't have any cats in the sky around here, so that's not going to happen. Probability of 0. Right? When rounding probabilities, when we're working with probabilities and we need to round an answer, right? It's better off to give an exact fraction, or if you have to round off, go to 3 significant digits. Now, since probabilities are going to be decimals, 3 significant digits means 3 places. So the probability of some event would be 0.x, x, x, 3 places, whatever those numbers are. Okay? You can represent probabilities as percentages, and I see a typo there. I'm sorry about that. It is very common to discuss probabilities of percentages because people feel comfortable. If I said the chance of rain tomorrow is 25%, that feels much better than me saying the chance of rain tomorrow is 0.25, right? While both of these are legitimate ways to represent probabilities, I mean, I could even go as far as saying 1/4, right? Most people, when we're just commonly talking, they really like percents because that's just where they feel comfortable. So less likely to use those two. Mathematically, we tend to like, math-wise, those two. Because if I want to use a percent in a calculation, I've got to convert it to a decimal anyway, so just give it to me as a decimal and then life is good. Okay? All right. There are 3 common approaches that we're going to use for finding the probability of an event. There's the relative frequency approximation of a probability. Okay. Now, this is also sometimes called statistical probability or empirical probability. But basically what this says is that one way to calculate the likelihood of an event, to find the probability of an event, is to gather some data from the past and use that data to predict into the future. So we say that the probability of an event A is how many times did we see A occur in the past versus how many trials of the experiment did we witness. All right, let's take a look at an example here. So here's our examples about drug testing, right? And so I have here what is called a 2-way table. It has rows and it has columns, and each row and each column represents a different label. So all 4 cells in this table represent a relationship between the column header and the row header. So like, for example, this 45 right here, because this is in the first row in the first column, that means that we are talking about 45 individuals who actually used drugs and got a positive test result. Okay. This 5 here, that would be people who used the drugs but got a negative test result. Or if I wanted to, I could say that there were 50 people who used drugs. Similarly, wow, that's a big word to say. The second row is people who did not use drugs. We got 25 who tested positive, 480 who did not test positive. And what does that give us? 505 who did not use drugs. Okay. Could we also say that in total there were 555 people in this survey or in this study? Could I say that there were 70 total people who tested positive there were 485 people who tested negative. Oh, I can even dig a little deeper. Can you see that in this table, these two things that I'm highlighting in yellow are things that shouldn't happen? Okay. That 5 up there, we would call that a false negative because the answer to the test was negative when it should have been positive because those people used drugs. And that 25 down there, we would call that a false positive because we had 25 people who tested positive but didn't use drugs. Now these two numbers that I'm highlighting in pink, those are correct responses or correct outcomes from the test. That 45 is, I used drugs and I tested positive. Or that 480 is, I don't use drugs and I tested negative. Those are the correct or accurate responses. Okay? All right, let's see if we can make some sense out of this though. Now that I understand how that two-way table works, I want to start answering these questions down here. First one asked me, find the probability of selecting someone who got a result that is a false negative. Okay, so what was the false negative? Oh yeah, the false negative was this, right? And so what's the probability of a false negative? Well, probability always starts out as a fraction. The numerator is going to be how many times we saw that thing, in this case the false negative. We saw that 5 times. And then how many people were tested? Well, the total number of individuals tested is 555. It's not the 480 who got the negative test results. It's not the 50 people who used drugs. It's 5 people out of everybody. The observed trials of the overall experiment, okay, which is everybody who submitted for this drug test. So that's 555. Now, that's a terrible fraction. I know that there's at least one person going, okay, we'll reduce it. Call it 1 out of 111. You're not wrong. I would argue, though, it might be cleaner to write that as a percent and call that 0.9%. So how often does that happen? Looks like it's less than 1%. Hey, who would suffer from a false negative? I don't know. Why are we testing these people for drugs? Are these people going to be operating heavy machinery? Then a negative test result, and if you're on drugs, that means that it said no, you were on drugs, and if the drugs somehow affect your ability to drive this heavy machinery, you might end up hurting somebody. So I guess it would depend on why we were testing, but the false negative says you didn't when you did. Right? All right. Question number 2 asks us to do basically the same thing, but this time find the probability of a result of a false positive. So the probability of a false positive would be the number of people who got a false positive, which we said was 25 out of that 555. And again, I'm going to argue for the decimal or the percent. So 25 out of 555, 0.045, so 4.5%. Now, who would suffer here? Oh, this one's a little bit easier to see who would suffer. If I didn't get the job because the test said I did drugs when I don't do drugs, I would suffer. Because I didn't get a job that I should have gotten, assuming I met all the other qualifications. A little bit easier. All right. Last one, and then I think we might stop here and break the video into 2 there. All right, last one, they're going to ask us to find the probability of someone who does not use drugs. Okay? The probability of no drugs. Well, I'm pretty sure at this point it's going to be something out of 555 because that's everybody. So who didn't use drugs? Well, the answer isn't any number in the table that was given to us. The answer is that's how many people didn't use drugs. It's all the people who didn't use drugs, so everybody who lives in that second row. So that's going to be 5 out of 555. I'm going to call that 505 out of 555. And it's, what is that, 91%? So 91.0%. What just happened there? 91.0%. Okay, just a note about this. The decimal on the calculator is 0.9099, 099, 099, and so on and so forth. So 0.9099099, and so on and so forth after that, right? We're supposed to go to 3 decimal places, which would be to here, which means that when I round it, I get 0.910. Do you see how I kept that trailing 0 on there? I didn't just call it 91%, called it 91.0%. That trailing 0 becomes significant because it's telling the world that this was rounded to 3 decimal places before it was converted to a percent. So round to 3, then convert. All right, I'm going to stop the video here. We'll come back and do the rest of it for part 2.